much like myself, she grew up in Modesto. She went away to college and found herself back here. And it's a great place to be. And she went to high school at Modesto Christian, but then went away to college at Calvin College in Grand Rapids, Michigan, where she got her BA in mathematics. From there, she went to Western Michigan University, and she got her secondary certification in teaching math. After that, she wasn't done. So she went to Stanislaus State. So she came back home, went to Stan State, and received her master's in mathematics, language, and cognition, not just math. She was interested in how people process math as a language, because it really is a language, and it's the language of science in a way. So, without any further ado, here is Heidi Meyer.
Thank you for coming. Wow, it's a Friday night, and I've got all these people here who want to hear about math. That's amazing, because, you know, most of the people I talk to, they say that they hate math, or they're afraid of math, or whatever the case may be. So we're just going to go ahead and get started. Infinite possibility, the importance of mathematical play. Good. Okay. Now, typically when I meet somebody new, whether it's at a gathering or if I'm at the grocery store in a long line and I'm talking to the person behind me, and we get to the point of saying, well, what do you do and what do you do? And I say, oh, well, I'm a math teacher. Immediately, I get the same response every time. They're afraid. But the interesting thing that happens is almost always, as the conversation continues, we start to talk about math. And it's not because I bring it up, it's because the other person has some questions for me about mathematics. So it's kind of like people have this fear, or yeah, they don't like the math, but there's still a little part of them on the inside that wants to talk about mathematics. And you know, when we're little kids, we don't hate and fear mathematics. Kids play counting out games. They play with shapes and images. They play eeny, meeny, miny, mo, and you count, and then you play tag. And there's even some cool games like this where you can predict your future, whether you're going to live in a mansion or an apartment, right, or a shack or a house. So kids have fun with math. In fact, I was visiting my nieces today, and my sister was talking with them, and she said to her daughter, well, what's 2 plus 2? And Sierra said 4, and she was all excited. So math is a really cool thing for her. But pretty quickly, math starts to look like this, and then there's this hanging over your head. And not too far down the road, it starts looking like that, and then it all starts feeling like it's coming at you like this. Okay? And then you look into the future, and all that you can see is this. And pretty soon, the entire face of mathematics looks like that. I see you can identify with this. Okay? Yeah, so what I'm hoping to do tonight is actually to exchange this space for another one, or at least move in that direction. And there we go. So what happens when I have a conversation with somebody about math who has told me that they're terrified of it, they hate it? Often what comes up, though, is they'll say, but you know what? There was this question when I was in 4th grade. This teacher put this thing on the board, and it was about a farmer with a boat, and he had to go across a river, and he had these things that he had to get to market. Maybe you guys are familiar with this. There's a fox, some geese, and some grain. But the farmer can only put one of these items in his boat at a time, so he's limited. But if he leaves the fox with the geese is going to eat the geese, right? And if he leaves the geese with the grain, then the geese are going to eat the grain, so how's the farmer going to do this? So we stand there in the checkout line at the grocery store, and we talk about how to do this. Another problem that comes up, strangely enough, they always say, when I was in 4th grade, my teacher put this thing on the board. Must be something about 4th grade, I don't know. But they say there was this envelope shape. And my teacher said to me, you know, take out your pencil and see if you can trace this without lifting your pencil and without missing one of the lines. You were given a packet as you came in, and there is a yellow card inside that packet. There's also a pencil. And on one side of that yellow card, you'll see a couple of shapes that look like this. So I'd like you to take a moment to try to do what I just explained.
You mentioned that they could lift up. A lot of them don't know that.
Oh, okay. And by the way, the seats have little desks with them. They're on the armrest, so you can lift that up and over so that you have a hard surface to work with. Before the end of the night, in fact, within about 5 minutes, we're all going to be able to do this successfully. But we're going to explore together how it is that you can do this. But I want to ask a question. Those of you that were able to do this successfully, if that's what I had asked you to trace, what do you think? Would you have been able to do it? Or how long might it have taken if there is a path? Long time. You have to try it, start someplace else, try it again. You'd have to get really, really lucky to find a path in this the first time. So what we're going to do is use a problem-solving technique that's really powerful, and that is to state and solve a simpler problem. And this is at the bottom of the same side of that yellow card. So we're going to make it much simpler. We're going to look at just a square, and then a square with one diagonal, and a square with two diagonals in it. So what do you think about the square? Is that traceable? You're going to have to work real hard at that? No. In fact, you can probably see it without having to try too hard. There we go. Well, I'm trying to hit the square. I think this is a bigger challenge for me than it is for you. Okay, here we go. So you can start at any of the corners you want, right? And you just go all the way around. And I'm sure you did a much neater job than I did. Okay? But now let's try this square in the middle that has one diagonal drawn in it. And I'm going to start up here in the top right. And I'll go around the square. And let's see, I'll go up the diagonal. Uh-oh, I'm stuck. Huh. Well, should I try maybe a different way, or do we think this one is impossible? A different way, okay. Okay, so let's try a red felt tip pen. Where should I start? Bottom right, okay. And then let's see, let's go up the diagonal. Oh, and then I can just go around the outside square. And that worked out just fine. I didn't get stuck this time. Okay, so let's move over to this last one. Looks like all the corners are about the same. So I'm just going to go ahead and start up here. And I'll go around the square and down the diagonal, and what just happened? I got stuck. Okay, so this getting stuck is the problem. We need to not get stuck. And the issue is, if you get in to one of these points or dots, I put a little note up here because I'll go back and forth between calling them dots and points and vertices. Those all mean the same thing. And then lines and edges mean the same thing. So you probably hear me using the words vertices and edges because those are the mathematical terms. As long as I can get into a vertex, I need to be able to get back out again. Otherwise, I'm going to get stuck. And this idea of in and out has to do with pairs. So going back to this one in the middle, got to find out where I am. There I am. Okay. This top right-hand corner in the center, that vertex has two edges coming out of it. So this one is even. So I'm going to put an E there for even. Down in the bottom right-hand corner, we've got three edges coming out of that vertex. So this one's odd. Put an O there for odd. This one also has two, so I've got another even. And then we have three up here for another odd. Now, there are some situations where I don't have to be able to get in and out, and I'm not going to end up being stuck. For instance, where I stop, where I end up, I don't have to get back out again, right? Once I get in there, that's okay, and I can stop because I'm done. And also where I start, I don't have to get into that dot, I'm already there. So the only places where I could possibly have a dot or a vertex with an odd number of edges coming out of it is at my starting place and at my stopping place. And that's why, for this one, we needed to start here, or we could have started down here and it would work because I'm already in, let's see, I'm kind of out of colors here, but in and out. Then over on the bottom left, in and out. So there's a pair, and I'm good there. Then up here, well, I used it already, but there's still an in and an out. And then I'm over on the top right now, in and back out. And then I get to the bottom and I'm stuck, but what? I'm done, so I don't need to get back out. Okay? Now this one worked. All of the vertices are even. Each one of them has two edges coming into it. And it didn't matter where we started at all, because I can just go all the way around. I can get in and out of wherever I go. But the situation over here, what do we have? They're all odd. So I'm going to end up getting stuck, because the only place I can have odd is where I'm coming in, or where I'm starting and where I'm finishing. Okay? So there are some really simple ideas that are at the heart of this. It's really all about avoiding being trapped. You need to be able to get out of wherever you go in. Getting in and out once requires a pair of edges. Pairing has to do with even numbers, right? 2, 4, 6, 8. Those are the kind of numbers we need in order to have a pair. But there are two places where you don't need to always be able to get out or get in, and that's at the beginning and the end. So you could have odd vertices at the beginning and at the end. So here's the conclusion. If there are 0 or 2 odd vertices, then the graph can be traced, or in mathematics we call that traversed. So let's try this one again. See if you can use the rule that we just talked about. Figure out which vertices are even, which ones are odd, if there's a certain place that you're going to have to start. Well, I know some people did solve this one earlier, so I know it's doable. Where do we need to start? Lower right hand, because this one is odd. It's got 3 lines coming out of it. I really can write better than this. Okay, or couldn't we have started over here on the bottom left also? Okay, and then it's going to work because all the other vertices are even. Here I've got 1, 2, 3, 4 lines coming out. That's reflected on the other side. It's symmetrical. And up top we have 2. So let's see if I can get my highlighter back. I'm going to start down on the bottom left, go up and across, and oops, up the top flap, down, over, up, and back across. Now I'm stuck, but that's okay because I'm done. Okay? So on the back side of your card, I have a couple of other images like this. So I want you to tell without tracing if it's possible to do this one or not. Don't try it. Look at it and see if it's doable. Okay, I see people nodding their heads and they're kind of pointing. Those 2 that I've just circled in red, those are the odd ones, right? And they're the only odd ones. So as long as you start at one of those 2 I've circled in red, you're going to be able to trace it. I know you're curious, so take a minute to go ahead and try that. Then we'll move on to the next one and we'll do the same thing. You're starting at one of the red ones, right? Because otherwise it's not going to work. I don't know if there are any left. Are there? We're all out, sorry. I'm just going to go across, and then I think I'm going to go around this diamond in the middle. And then I'm going to go around the square on the outside. And then I'm going to head back into the middle. I'm going to come down, up the diagonal, down, up the other diagonal, and I ended up in the other circled vertex. It will work. If it didn't work for you right now, try it again at home. I bet it'll work better. Okay, taking a second look at some things sometimes helps. Okay, what about this one? Can you tell without trying it? Can you just look at it and see if it's doable or not? Yeah, okay. Does it matter where we start with this one? No, because they're all even. So one approach would be to do the triangle that's in the middle. and then trace the triangle that's on the outside. Okay, that'll work. I'm going to switch colors here. We could also start on the outside, and I want you to notice something. I do have to be a little bit wise about my choices. What's going to happen if I go all the way to the top? I'm not going to be able to finish it, so I have to exercise a little bit of wisdom and go around this triangle in the center, and then I'll be able to go up and finish it off. So you can start from any point on this one, and you're able to trace it. Well, here comes this one again. What do you think? Now that one's not on your paper, so you got to look up at the front. Is that one traceable or not? Yeah? Because it looks big and intimidating, right? So it has to work. Math by intimidation, it works every time. So somebody convince me. You're kind of losing track? Okay. I'm gonna focus your attention on 3 vertices. Check those 3 vertices out. What's true about all of them? They're odd. Can you trace it if there are 3 odd vertices? No. Actually, no, because we could only have 2, our starting place and our ending place. Otherwise, we're going to get stuck because we won't have an out for an in. In fact, there are even more odd ones. So this one is not traceable. We could have sat here for an hour and tried this over and over and over. I'm going to find it. I'm going to find it. There must be a way. But there's not a way. So this rule has given us the power to be able to figure that out. So, you know, I think this is kind of fun. And other people obviously do, because like I said, when I'm standing in line at the grocery store, they'll say, you know, when I was in 4th grade, my teacher gave me this problem, and can you tell me how to do it? So for 20 years, they've been thinking about this and still want to know the answer to it. But is there any application for this sort of thing? And there really is. There's tremendous application for this. Graphs, collections of points and lines can be used to do modeling. So in a field like linguistics, which seems very different from mathematics, city planning, traffic flow, garbage collection, if you think about deliveries that need to be made, postal routes, that sort of thing, street sweepers, they need to be able to go down every single street, and we really don't want them, you know, going up and down the street 5 times, because that's going to cost more in terms of money and time. That's going to get passed on to their employer, which gets passed on to you. Right? Now that's going to be a little bit of a different problem if we're talking about a street sweeper or garbage collector, because they have to go up and down each street, not just once, but twice. So the graph's going to look a little bit different. Representations in computers, communication, data organization, all that sort of thing, modeling in physics and chemistry, minimization of network length, anything from laying railroad tracks to connecting computers together. But also, it's used for solving other puzzles, and here are some of them. You may have seen that one up on the top right recently in a movie. Rise of the Planet of the Apes was one of the tests that they used for intelligence. That's called the Towers of Hanoi, and I think in the movie they called it the Lucas Towers. This is a puzzle called Instant Insanity. Doesn't that sound like fun? I think this is a little bit like the Rubik's Cube. It was first marketed in the 60s, and it kind of comes back in, and then it goes away again. But this is a puzzle. It may not look that difficult to solve, but there are actually 41,472, I think it is, different ways to line up those cubes in a row. And the goal with this is to have all 4 different colors showing on the front, on the top, on the back, and on the bottom. Okay, given that there are more than 40,000 ways to do this, trial and error is probably not a really good approach, unless you're really, really bored. Okay, and on the bottom, this is a puzzle from pure mathematics, which is called the 4-color theorem, and that also has graph theory that can help to solve it. So I'm going to unveil what the graphs look like that would solve these. For the Towers of Hanoi, you could make a graph like this, and that would contain all of the moves, and it would also show you what the solutions are. For the Instant Insanity puzzle, one of the hard things about that is you've got these blocks, And it's really hard to see because it's three-dimensional. You can't see the back and the bottom at the same time you see the front and the top. You can represent each cube using a graph, and then you can put all of those together. And if we had more time tonight, I could explain to you how to take that apart and read it so that you could put the 4 blocks in a row in a way that solves the puzzle. The next one, I'm just going to enlarge the graph that's already up there. So to me, it seems like this idea of graph theory would be something that's been around just forever, right? It's just points and lines. And we can use points and lines to represent things like streets and locations. This actually had a starting place, and it's not all that long ago. It's the 1730s. But it started in a place called Königsberg. It's now Kaliningrad. And through this city runs the river Pregel. And it's got 2 islands in it. And these islands are connected by bridges to the north shore, the south shore, and to each other. And this is back in the 1730s, so there was no television. Nobody had to tell anybody to turn their cell phones off, right? So what people would do for entertainment on a Sunday afternoon is they would go downtown and they would challenge each other and see if they could walk across the bridges exactly once without missing a bridge and without going over a bridge twice. That should sound a little bit familiar. Let's join the people of Königsberg. Oh, there we go. So those are the bridges you got to get across. So the soldier's going to try. See how he does. He gives up. Yeah, I heard somebody say, oops. You could tell before he even fell over that, no, this is not going to work. But just because that one path didn't work doesn't mean that he shouldn't try it from a different starting place. There are lots of different ways to start. And you know how it is. If you're walking with friends and you're kind of window shopping, you think, oh, did we go across that bridge already? Or was that last week? Or did we miss that one? So this problem came to the attention of mathematician Leonhard Euler. And what he asked is, what's important about this? What is it? Is it the temperature of the water and how fast it's flowing and how tall the buildings are? Is it how the streets are laid out around the area? No, we really don't need that. We really just need to focus on the bridges and the locations. And in fact, we don't even need something as complicated as what you're seeing up there right now. We could break it down even further. Now, I think it's not too hard to make the leap from this image to this image. The next one is a little harder for a lot of people, but it represents the same thing. This dot represents the island on the west. This dot represents the island on the east. This represents the entire North Shore. I don't need to know that that North Shore is this big. I just need to know that all 3 bridges connect to it. Okay? And this dot down here represents the South Shore. So if I asked you, can you trace this without lifting your pencil, without skipping a line, without going over a line more than once, it's the same thing as asking, can these people walk, across the bridges without missing one. I'm going to move to the next slide, which also has that same image. So if you're counting, hold that thought. Okay, what do you think? Is this possible? No, why not? Because they're all odd. So we're going to give it a good try. I'm going to start someplace different than the soldier did. Yeah, that's way over there. I'm going to start down here, maybe go this way and come back around. Maybe I think I can do a better job than he did or something. No, just as you guys knew, I would end up getting stuck, right? I'm stuck over here. I can't get out because this is an odd vertex and it doesn't have an out for the N. Okay. So if you read the flyer for tonight, I said that I was going to be talking about tracings and tangles and tilings. So that was tracings, and we're going to move on to tangles next. And by tangles, I mean knots. Knots have been a part of human culture for pretty much as long as there has been a human culture. If you take a look at the pictures behind me, it's part of our artwork, it's part of our work, it's part of our textiles, it's part of our stories and our mythology. And in fact, what we know now is it's part of every cell in our body, right? Because we've got DNA knotted up very small in every single one of our cells. Boy, you guys are good. What a good audience. I hear you going for those packets because you know that there's something else in there that we're going to be doing. That's awesome. Okay. Knot theory, for as long as it's been around in terms of human beings tying different sorts of knots for different sorts of purposes, that's been with us for pretty much as long as we've been around. But in terms of a mathematical consideration, that's really quite recent. It's only about the mid-1800s. There was a little bit of writing done in the 1770s and then a little more in the 1830s. But when it really became of interest to mathematicians is in the mid-1800s, when scientists were looking for a way to model the atom. And scientists who thought about modeling the atom potentially as a knot was Lord Kelvin, who you may have heard of because of the Kelvin temperature scale, okay, with absolute zero and all that. He thought that perhaps atoms could be best modeled by knotted vortices in the ether. Back then they had this idea of the ether that was pervading the universe. This is by no means a complete historical model, but just to give you an idea, back in ancient times they were already talking about perhaps an atomic basis to our universe. And then up into the 1800s things got really active with that, with Kelvin's idea of knotted ether. Then we have Thomson's plum pudding model, which includes the electrons, but they thought they were just kind of stuck in there like raisins in pudding. Okay, and then the Bohr model, and then we've moved on from that with quantum theory and so on. So when this idea of Kelvin's came about, mathematicians got really excited. Mathematicians are very excitable people. They do like to play, and they just took to this with gusto. And they started making tables of knots, and it's a pretty tricky thing to do though. It's hard. What they needed to do was discern, well, this knot has 5 crossings and this other knot has 5 crossings. Are they the same knot or not, So, and well, how can you not have a knot pun in a talk about knot theory, because it just happens. So these tables got pretty complicated, and you can see up at the top we've got a 3-crossing knot that's called a trefoil. We're going to be working with one of those pretty soon ourselves. And it just keeps going from there. So in fact, as you go, the number of different knots becomes larger and larger. So for 3 crossings, there's only one 3-crossing knot. For 4 crossings, there's only one. For 5 crossings, there are 2. For 6 crossings, there are 3. If any of you are familiar with the Fibonacci numbers, kind of looks like the Fibonacci sequence is starting up. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is, that next number should be 5, but it's not. One of the open questions in knot theory is whether or not there's a formula that governs this list of numbers, and whether or not I could say, well, for 17 crossings, there are this many knots because I need to use an exponential function and then do this thing and this other thing, and that'll tell me how many there are. But we don't know that. That's an open question. Here are some examples. The knots up at the top, those are 2 different knots that both have 6 crossings. And what I mean by different is if you create these knots out of string, you cannot push a loop through another loop and tangle and twist and turn it upside down to turn one of these into the other one. They're never going to look exactly like each other. You can't do that. But these 2 knots on the bottom, these are called a Perko pair. These were first tabulated in 1899 as being 2 different knots with 10 crossings each. And it took 75 years for somebody to notice that those are actually the same knot and not different knots. 75 years, so this is not easy work. And that was a recreational mathematician, by the way. He was a lawyer by profession, actually, and his name was Perko, so that's called the Perko pair. So we're gonna do some playing, but I want to give you a word of caution. If you've ever been fishing, or if you've ever had a bad situation with your shoes, you know what can happen when you're working with strings and tangles. So I'm going to have you follow directions with this really, really closely. We are going to make the trefoil knot. You do have some string in your packet. You will also need I'm going to back up just a second to point something out. You will also need the little white sticker that's in your packet. Okay, so you need a string and a sticker. The reason that you need the sticker is that mathematical knots don't have loose ends. If you take a look at these examples that I have up on the string, you'll notice that it's a closed loop. They don't have loose ends, which makes them truly knots, because it's the loose ends that you need to be able to untangle things, right? So we're going to make the trefoil knot, but it's also called the shoestring knot. I hope you guys did not grow up just having Velcro shoes. I hope you've all tied your shoes at some point. So you need to take your string and hold it up like this so that it looks like a U. Then you're going to cross the two ends over each other, and then you're going to push one of the ends through, just like you were taught when you first learned how to tie your shoes. Okay, I'll do that again. You're going to hold it up like a U. Then you're going to cross the ends over each other. Just put them across. And then you're going to take one of those ends and you're going to stick it through the loop and pull it back up again. So it looks like that. I feel kind of like an airline stewardess. So what I'm going to suggest is put on your own oxygen mask first. And if somebody next to you needs assistance, then please render assistance to them. Once you have it knotted in this way, then take your sticker and use it to close up the ends so that you have a closed loop. Okay, so as I said, go ahead and do your own, but then if you see somebody near you struggling, please do render assistance. So what it should look like when you get it tied and closed off, it should look like what's up on the screen. Thumbs up? All right, thumbs up. Okay. So, well, now that I've already given you one challenge, I'm going to give you another one. We're going to turn this into another knot that is actually the same knot. We're going to change it just a little bit into the trefoil knot, which looks like a three-leafed clover. And you have to kind of shake it, yeah, like that. You have to kind of just shake it and jiggle it and let it fall into this. Now, it may not seem to you at first glance that these are the same, but if you look at them, they both have 4 regions. The first knot you tied has 2 huge regions, and then right in the middle there are these little tiny pieces. But if you look at the trefoil knot, you've got the 3 loops on the outside like petals, and then you've got that 4th one in the middle. They both have 4 regions. So you just have to kind of shake out those middle regions so that they get a little bit bigger and spread it out. Okay? And again, with the oxygen mask. Right? Get your own first, and then if somebody around you needs assistance, gently offer to provide it. So what we're shooting for is that 3-leafed clover. It's called a trefoil knot. It's also called a shoestring knot. The knot that I tied, which is the one that you see up on the screen, is a right-handed trefoil knot. And what I'd like you to do right now is to take your knot and put it so that the single loop is facing me and the 2 loops are facing you, so it looks like it's oriented like mine is. We need them all oriented the same way so that we can talk about this. No, we're talking about the same thing. Okay, so your 1 loop should be facing me and the 2 loops should be facing towards you. And we're going to focus our attention on the crossing that's in the upper right. So look at the crossing that's in the upper right. Notice that on mine, the vertical strand goes over. And this is what's called a right-handed trefoil knot. If your strand up on the upper right is going over instead of under, this is a right-handed trefoil knot. Raise your hand if you got a right-handed trefoil knot. Okay, quite a few people, good. But we also have a left-handed trefoil knot, and that is where you've got an undercrossing. So let me see a show of hands again, because that'll tell me, okay, good, good. So I know almost everybody has a knot, so that's a good thing. Before we move on, I want you to take a moment on your yellow card to record which one of these you have so you don't forget. I'm going to tell you what's supposed to happen. Actually, this one, you can turn the one into the other. So I took that one loop, I flipped it over. My next move was going to be to rotate it 180 degrees and just spread it out a little bit, and you do get the left-handed knot. In fact, the two pictures I had on the other slide, it was a before and after. Before and after I had done this. So I'm not sure why this is freezing on me, but okay. What I would like you to do is to try to do something like that with your trefoil knot, remembering what it was you started with, and see if you can take your right-handed one and turn it into a left-handed one, or your left-handed one and turn it into a right-handed one. So just, and be a little gentle with it, because your ends are put together with a sticker, so it might come loose. So just kind of move it gently and see if you're able to change it from one to the other. This is why I had you write down what you had to begin with. Something that's called chiral, which comes from the Greek word for hand, and these two knots are inherently different from each other. We see things like this in science as well when we're studying chemistry. There are some molecules that are known as chiral, which means that it matters whether you have a left-hand version or a right-handed version. And there are some that are achiral or amphichiral, which means that they can be turned into each other and that the right-handedness or left-handedness actually does not matter. This one is chiral. If you've got a right-handed one, it's going to stay right-handed. If you've got a left-handed one, it's going to stay left-handed. So some applications. I want to tell you a little bit more of the story, because the title of this talk is Infinite Possibility, the Importance of Mathematical Play. What happened is that Kelvin's knotted model of the atom held sway for about 20 years, and people went nuts with knot theory. They were tabulating stuff left and right. It was just crazy. But then it was found that this was not actually a good model for the atom, and so there was no known application whatsoever for math theory. But mathematicians, being the playful people that they are, just kept playing with it. And what's really cool is then later, in 1953, when it was found that the DNA exists in the double helix form, then knot theory and related aspects of topology came into play, and those can be used to describe what goes on with the DNA. Similarly, I mentioned chemistry and molecular structure. And interestingly enough, with the physics, we've kind of come full circle, because Kelvin thought that perhaps atoms were knots, but now we have a model that has electrons, protons, neutrons, quarks, all of those sorts of things, but we're pursuing string theory, which is making it look like there's perhaps vibrating strings that are at the heart of everything. So we're kind of back to knots being at the bottom of everything. It's a pretty big branch of mathematics. There's actually a journal that's dedicated just to knot theory and its ramifications. And if you are someone who is yet trying to decide what to go into, let me tell you, this field is wide open. There are a lot of unanswered questions. A very recent, very big breakthrough was in 1984. It's called the Jones polynomial, which is something that mathematicians can use without having to do trial and error to figure out if knots are the same or if they're different. So it might be something that you want to look into at some time. So far we've seen tracings and tilings. I've got one more thing that I promised you. I'm sorry, tracings and tangles. We're going to move on to okay. And the person most associated with this for me is someone you're probably familiar with, and that's M.C. Escher. I imagine most, if not all of you, have seen some of his work before. A lot of his work displays mathematics, and I'm just going to run through a bunch of it. This is not a tiling, but that's a mathematical object called a Mobius strip. Here we've got some mathematics going on in terms of two-dimensional versus three-dimensional, but also the issue of self-reference. How did those hands get there to be drawing themselves in the first place? Right? Kind of cool. Just some mathematical shapes there, polyhedra, stellated polyhedra. This has the idea of limit to it, but it's actually also related to an idea from non-Euclidean geometry called a Poincare disk. So Escher had all kinds of mathematics throughout his work. If you've never seen this one before, take a moment to see what's going on with the water. Where is the water at the top of the waterfall coming from? The bottom. This is, right, perpetual motion machine that we've got going on here, right? Because the water from the bottom is flowing to the top and falling back down and flowing back up to the top again. This is based on an image created by a recreational mathematician. He's actually a well-known physicist named Roger Penrose. It's called the impossible triangle, and if you look at the picture of the waterfall, you can see that there are two of those triangles in there. Escher and Penrose actually interacted with each other quite a bit, and Escher's artwork influenced Penrose's mathematical work and vice versa. So they really influenced each other. I want to just bring to your attention, there's an interview in Discover magazine from September of 2009. You might want to just jot that date down if you're interested. But they were interviewing Roger Penrose, and his father was a mathematician. And so they asked him, well, how did your father influence you? And his father also made wooden puzzles. And he said, well, for my father, there was no boundary between his work and his play. And that's what most impacted me. So there's that playfulness coming out again. This is similar. In fact, the story behind this one is Penrose showed his father the impossible triangle, and then his father came up with the impossible square, or the Penrose staircase. And you may have seen this in a recent movie as well. The movie is Inception, where they get inside of people's dreams and stuff. And so this next scene shows one person teaching another person kind of the architecture of the dream world.
You're gonna have to master a few tricks and build 3 complete dream worlds. Excuse me.
What kind of tricks?
In a dream, you can cheat architecture into impossible shapes. That lets you create closed loops, like the Penrose steps, the infinite staircase. See? Paradox.
I don't know if you heard that last word or not, but it was paradox. So hold on to that last word. Okay. This is a quote from Escher, and I've bolded the pieces that I think are the most important. By keenly confronting the enigmas, in other words, the puzzles or the paradoxes that surround us, and by considering and analyzing the observations that I had made, I ended up in the domain of mathematics. Although I'm absolutely without training in the exact sciences, I often seem to have more in common with mathematicians than with my fellow artists. Well, how did that come about? It's in that first line, which is that he was keenly confronting the enigmas or the puzzles or the paradoxes that surround us. So to get to the tilings, this is one of the things he's famous for. Technically, we call them tessellations. Tessellations and tilings mean the same thing. It's kind of an interesting thing, right? Angels and demons. Tiling. Birds, dark birds going one way and the light birds going the other way. And then that last slide you saw was a study, and then he incorporated it into this piece. So we're going to finish up by understanding what it is that allowed him to do that. How did he figure out what would tile? What would work in order to tile? We need to talk about angles and polygons in order to do that. And I'm going to limit this. There are different types of tilings. We're just going to look at regular tilings. You can also take different shapes and tile them. We're not going to go there tonight. You can look that up on your own if you're interested. We're just going to consider triangles with triangles, squares with squares, and so on. So in a straight line, 180 degrees. Okay? In a circle, 360 degrees. How many degrees are there in a triangle? 180. How do you know? More math by intimidation? Some teacher way back when told you that that's how many angles are in a triangle? Well, you know, there's a lot of different triangles. There are short ones and tall ones and wide ones and scalene ones and all of that sort of thing. In your packet there's a triangle. Everybody's triangle is different. I cut them out by hand. They are all unique. They are all different. Okay. Here too, you have to be a little careful. In just a moment, I'm going to have you do some tearing. But you want to be careful when you do it because I need you to tear off each corner. And if you happen to have a really skinny triangle, it might be hard to do that without tearing into the other angle. So you need to tear it so that you still leave enough on that edge so that you can tear off the other corner. So because if you cut the corners rather than tearing them, you're not going to be able to tell what the corners of the original triangle were. So just tear them off. Okay. So here's my first one. I'm going to do another one just for comparison. Now once you have all the corners torn off, what I'd like you to do is put them all together in a point. So make all of the pointy ends, put all the corners together so that they come together in a point and see what happens. My fingers are sticky, so mine are moving around. What are you seeing is happening? You're getting a straight line. How many degrees are there in a straight line? Okay, and it's for that same reason that we have 180 degrees in a triangle, because if you add up all the angles, if you put them all together, you get a straight line, which is 180 degrees, okay? And I've got my two examples up there. They're a little bit hard to see, but I hope that you can see that straight line going on in there. So the question is, how many degrees are there in other polygons? But what I'm really concerned with is how many degrees there are in each angle of a regular polygon. So the polygons, we're going to again restrict ourselves, and it's just going to be to polygons that have the same length side or the same angles all the way around, like this triangle you see, you don't see. I got to switch this thing. Okay, there we go. Okay, so triangle, 3 angles. So there are 60 degrees in each angle, right? Take the 180 and divide it by 3, you get 60. Well, what about a square? Well, you can take a square and cut it into, cut it into 2 triangles, which is 360 degrees, but there are 4 angles. So 360 divided by 4 is 90, which should not be a surprise because you know that squares have 90-degree angles. Okay, we're going to do the same thing with a pentagon. That can be cut up into 3 triangles. If you multiply 180 by 3, you get 540. But then divide by the number of angles there are, and you get 108. Okay, so there's 108 degrees in each individual angle of that pentagon. Okay, way up at the top, that angle there, if you put a protractor on it, you measured it, that would be 108 degrees. Okay. So here's just a list of some of the degrees from triangles up to octagons. And there's a column that's left open, and that is, will it tile? Yes or no, will it tile? So we're going to check some of these. Could I tile my kitchen counter using triangles? Yes. Okay. They fit together very nicely. Eventually I'm going to ask you about hexagons. Given what this is looking like right now, especially if I take these 2 away, what do you think is going to be true of hexagons? They're probably going to work also, okay? I'm going to do this next one super fast because you guys already know about this one, because you know what a checkerboard looks like, right? So the squares are a yes. Okay. Then I have some pentagons. Okay, I'm going to try to do it with these. And I try to fit that next one in there, and well, it's too big, so I'll fit it over here, and then I'll try to put this one over here. That's not going to work. Okay, pentagons aren't going to work. Hexagons. Well, we kind of saw that with the triangles. In fact, you already knew this if you've ever seen a honeycomb. Okay, so those work. They can go together without leaving gaps or overlaps. They could tile. You could tile your counter with it. A 7-sided shape is called a septagon. What do you think? No. Probably not. You've probably never seen anybody's counter tiled in septagons. Probably never heard of them before. They're 7-sided polygons. Yeah, that doesn't fit so well. That's not going to work. What about octagons? Stop signs. Yes? Okay. They actually can make a pretty cool tiling, but not all by themselves. That's not going to work. Now, I could do it if I were to put a diamond or a square in the middle. Okay, but we're only talking about the ones that tile with themselves. So the only ones that worked were triangle, square, and hexagon. And the reason for that is for something to tile, it has to come full circle. It has to go 360 without leaving any gaps or making any overlaps. So here's our chart again. They've got to go 360. They've got to go full circle for no gaps and no overlaps. Okay, so if I fill out my chart, triangle, each angle is 60 degrees. 6 of those gives you a 360. Square is 90 degrees. 4 of those give you a 360. And you see 4 of them coming together right there at a vertex. With hexagons, you've got 120 degrees. 3 of those are going to make a 360. Okay. So what Escher would do is he would start with a polygon, but then he would morph it. So I'm going to start with a rectangle. I'm going to cut a triangle off the bottom and stick it on the top. Can you see that I could work with that like a jigsaw puzzle and that the top would fit into the bottom and that this would still tile? So I can tell you, I started with a rectangle, which I know is going to tile, and then I morphed it. It's still going to tile. That's looking like a rooftop to me. So I'm going to put a chimney on it, a couple chimneys. And then I'm going to fill up the whole plane with shapes like this. And that kind of looks like a neighborhood to me. So I'm going to color one of them. Okay, that's kind of the idea. That's a very simple one. It's not anything like Escher's work, but that's kind of the idea. So here's, this is called a study in regular divisions of the plane with reptiles. This is based on a hexagon. And we're going to see an animation that shows us how Escher did this. So can you see where the pieces are coming from? It's a hexagon, but he's taking pieces out from the inside and he's sticking them onto the outside in order to make the reptiles. And then they're going to tile the whole plane. Okay, so it all starts with a polygon. It all starts with a polygon, and then you morph it and you turn it into other things. So there you see the hexagon superimposed on the reptile. That was just a study, and then he created this piece of art from that. And again, you see a number of mathematical things going on. The 3-dimensional object in there is a dodecagon. You've got the 2-dimensional reptiles, and then they pop out and they become 3-dimensional and they walk around and come back. Another image of birds, tiling the plane with birds. This was also a study. And here too you can see, so he had a triangle here. He cut out this piece between the wing and the tail and put it on this side for the head and so on. You can see where all these pieces are taken off and then hooked on the other side. And eventually that became the piece called Liberation. Can you see why it's called Liberation? Okay, pretty cool. And here are these birds again. These are based on a quadrilateral, 4-sided, and this became the piece Day and Night. So, well, and in terms of application, I thought this was pretty cool. I came across this just the other day, so there's a new slide that I added. And this is from Pappus of Alexandria, who lived from about 290 AD to 350 AD. And he was looking into these tilings. Bees were endowed with a certain geometrical forethought, there being then 3 figures which of themselves can fill up the space round a point, the triangle, square, and the hexagon, just like we saw tonight. The bees have wisely selected for their structure that which contains the most angles, suspecting indeed that it could hold more honey than either of the other 2. So the bees could have used triangles or they could have used squares in order to do this, but those wouldn't have held as much honey as a hexagon. So what I've been trying to share with you tonight, and I hope has happened, is to show you that math can be something that's playful. It's kind of like a really cool playground. In fact, I think that's how most mathematicians look at it. We think it's the biggest game in the whole universe. And the gate is open. You can enter. I want to show you a little bit of an overview. I think where we sometimes get tripped up is that we've got this pathway of arithmetic, and then we've got this front wall of algebra. And usually what kind of an entrance do you have to a castle? A portcullis, right, that could come down on you. But on the inside, there's all this stuff, fractals and infinity and set theory and game theory and the fourth dimension and all that thing. I have news for you. The portcullis is open. Okay, you can walk on in. It's not, you don't need to unlock it. It is safe to enter, and there's a lot of fun to be had there. I want to just briefly show you two other things. Four-dimensional because we inhabit three-dimensional space. So it's a three-dimensional shadow of a four-dimensional cube that's being projected on a two-dimensional screen. So it's a little hard to wrap your mind around, but it's worth it if you want to give it a try. Okay, so since we finally got that running, I'm just going to let that go for just a moment. Okay, this is a geometrical object known as a fractal. It's actually a graph. By the way, on the other side of that blue card is directions for making the impossible triangle. So if you want to go home and try to draw the impossible triangle and make cool waterfall shapes out of it and stuff, you have the directions for that on the other side of this blue card. Okay, and I can put this back up again pretty soon if you still need to get that information down, but I do want to get my thank yous up here. To Wes Page for the animations, and to Bill Van Riet for cutting out some blocks for me to use. So Wes created the animations from the beginning, and of the soldier, the bridges, and of the reptiles. And then Bill Van Riet cut out some wooden blocks for me, which was really cool. And I just want to welcome you to the playground of mathematics, and I hope you enjoy it.